The Norman Foster Foundation public debates are now starting.
Good evening everyone, and welcome to this, the first public debate of the Norman Foster Institute on Sustainable Cities. I'm Tim Stoner. I'm a member of the academic faculty of the Institute, and I'm your chair for this evening's debate. Our subject this evening is Cities Beyond Earth. Now, although the work of the Institute is strongly focused on planet Earth, the premise for this evening's debate is that there are lessons to be learned from the design of settlements off Earth. What will these places look like? How will they be built? And perhaps most importantly, how will they be used as human places? And we've three expert speakers who are going to share their thoughts on the subject. But before they do, I'd like to welcome the person whose creative curiosity, strategic foresight, and civic leadership is the bedrock of the Norman Foster Institute, Norman Foster.
Thank you. As a child, like many of my generation, with a childhood that overlapped the 30s, 40s, and 50s, I had an optimism, a delight. The future fired my imagination. And maybe I'm still a child. It still does now. And that optimistic view of the future, that excitement about a future which was brighter, shinier than the past, was inextricably linked to space flight. And perhaps it informs something that I've said from time to time, that the science fiction of my youth is the reality of today. And if I go back in time and I look at the imagery that fired my imagination then, it's remarkably anticipatory of the future that was realized. And the imagery, even the color of the spacesuits, is remarkably anticipatory of the reality that would follow. And the two children here, how long will it be before we travel by rocket airliner, is appropriate alongside the launch of Apollo 8 in 1968. And on that flight, Bill Anders took a photograph which has been called Earthrise. It's probably one of the most widely published photographs of all time. It was described by Nature at that time as the most influential environmental photograph ever taken. And it revealed for the first time what kind of future gurus like Buckminster Fuller were pointing out, and that was the razor-thin layer that protected planet Earth. And perhaps this had the shock of realization of the fragility of the planet. And 16 months later, on Earth Day, in America alone, 20 million people took to the streets. So the power of that image was absolutely extraordinary, a movement, of course, that continues today. And 50 years after that epic flight when the astronauts went up, orbited around the moon, came back, they took the photograph on the way, and 50-year anniversary, I think it was 2018, Bill Anders said, we set out to explore the moon, and instead we discovered the Earth. It's interesting to go back to the roots of NASA. NASA is the acronym for the National Aeronautics and Space Act of 1958. The key words that activities in space should be devoted to peaceful purposes for the benefit of all mankind. I think that it's just worth contemplating that this space age was not just about going up there and coming back. It had extraordinary side effects. So, 66 years on from that act, we have 2,000 spin-off technologies. We have 30,000 commercial applications. There is so much in our everyday lives which is coupled to space exploration that we take for granted and we never, ever think about. I mean, where would we be now without GPS? Artificial limbs refined through the technology of spaceflight. The diagnostic power of the MRI, which we take for granted. Again, another spin-off from space. The tiny camera in the phone that we hold, all directly attributable to spaceflight. The refining of solar cells through space stations, which inform, here for example, the solar farm at Masdar, 10 megawatts, which powers the entire community 24 days, 7 days in the desert. And that's only using about 40% of this capacity. And if we look at some of the technologies that come together in terms of the drone, and we think of drones in terms of military, but this is a humanitarian. This is Zipline, and Zipline operates in Africa and delivers vital supplies. It leapfrogs. It delivers medical supplies faster than if there was the infrastructure of roads. And interestingly, has gone on to now be applying a kind of contract with the National Health in the UK to deliver medical supplies to more remote locations. We know the founders very well, and one of the inspirations behind this project is a project that eventually led to a foundation project and was about drone ports that would relate to a drone facility and would become more than just a staging point to charge the drones, to house them, to maintain them, would have a social dimension in remote communities, rather like a kind of post office or a community center. And the idea was that you would use the materials that were to hand. In other words, you would use the soil in a local community, and you would use a kind of high-tech formwork, lightweight formwork, and you would drape 2 layers or 3 layers of terracotta-like, earth-made, using an additive with the soil, compressing it, no heat involved, a kind of dry terracotta-like tile, which would then harden, and the design of the dome, quite carefully calculated, would be stable to create cells which could cluster together. And this was an early visualization. It then became a foundation project that brought together 4 universities, one in America, 2 in America, 1 in the UK, and 1 here in Spain. And the students came together again with mentors, and we built a kind of proof of concept cell as part of the Venice Biennale. And for quite a few years, it was a permanent pavilion. It's since been removed. But you can see here that it's the highly optimized dome-like shape. And there's a very interesting link between that and the work that we did for the European Space Agency and NASA on habitations, lunar habitations. And this was the work on the Martian habitations with NASA, and here the lunar habitations with the European Space Agency. And what is similar is that they are both using the local material, mixing it with an additive to make a structural material, and then layering that. The soil is actually not soil, it's moon dust. It's called regolith. And that was tested by the team in vacuum conditions through a whole series of kind of working ground base using volcanic dust, which is the closest that you can get on Earth to planetary regolith. And here you can see the robotic devices which are manipulating that material. And you start to see the rather interesting honeycomb structure. And so the difference here robotically, as opposed to a community in rural Africa where you're actually wanting to empower the community to be able to self-build. But that geometry is very much linked into research into bone structures, animal bone structures, and human bone structures. Mark and Xavier, who are on the front row here and who will shortly be taking the platform, were both involved in these two projects, so there's a link. But leadership created everything that we're seeing here. It was the role of the individual that created all of this work, the idea of a structure that would be resistant to meteorites. All of this, all these kind of glimpse of enormous body of work comes right down to 1962 and Kennedy. And I think the words are appropriate beyond space. We choose to go to the moon in this decade and other things, not because they're easy, but because they're hard. Thank you.
Thank you, Norman. So, to our debate this evening, and the first of our speakers is Dava Newman. Dava is an aerospace engineer, former deputy administrator at NASA, and director of the Media Lab at MIT, and an honorary dean at the Norman Foster Institute. You're very welcome, Dava.
Thank you. Thank you. Thank you so much to Norman and Elena. It's so wonderful to be here. So let's take a journey throughout the solar system and then end up on Earth. And as I say, an exploration, and it is hard, and that's why we like it, because it pushes us to be excellent and to strive for excellence and to really turn that impossible future into possibilities for all of us here on Earth. So you might know about our James Webb Space Telescope. It's almost a miracle. It's imaging. We have the Hubble telescope that we've been using for 3 decades, and now with the Webb, Hubble is in the optical realm. And look at what Webb shows us. It unveils galaxies and exoplanets. So that's the Hubble image of these pillars of creation. You might know this image. And look at what the Webb image it's giving us. Look at those planetary systems and all those stars. So much more to explore for humanity. So I like to use this chart to put it to scale and to show you where we are. We are on the pale blue planet, the pale blue dot Earth. This is to scale. These are in astronomical units. We do have our scientific Voyager 1 and Voyager 2 to the edge of our solar system through the Kuiper Belt. And all of that, those are our close stars. You might see the Orion stars there and recognize some of those, but light years away. You've heard about exoplanets? We're looking for other habitable planets. We're looking for life. I think we will find it, evidence of past life. So our very first exoplanets were revealed here. 51 Peg B was the first exoplanet, and then Kepler-16. Now these are artists' conceptions of what would it be like on these other worlds. We know that these exoplanets, Earth-like planets, are out there, but we've been with our imagination, we've been with our scientific understanding. Of course, we've never been physically, because they're too far away. Kepler-16b is a binary system. So if you're a fan of Star Wars and Luke Skywalker, move over. Tatooine, yes, it's a binary system. We have binary systems, and we're discovering more all the time. 6,000 exoplanets we've discovered so far. The exoplanet science, it's only 3 decades old. You couldn't even major in something called exoplanet science a few decades ago. Now it's a booming field. And I really like the TRAPPIST-1 system. You can take a look at these 7 planets around the sun. They're all exoplanets. They're all possibly Earth-like and kind of the size of Earth in terms of planets. So they're wonderful places, again, to take our imagination way beyond where we ever thought possible, and this is real science. These are real systems. There's the artist's conception over there to the right. Let's come a little bit closer in. We have been to Pluto. I know it's a dwarf planet now, but I love Pluto. Why? Look at that heart on it. So our mission to Pluto took 9 years. We had never imaged Pluto. We didn't know what it looked like. Look at this resolution, and we got closer and closer and closer. Now we know the topography of Pluto. We know what it's made out of. We know the chemistry of Pluto. Jupiter. We have a mission right now to Jupiter. It's called Juno. That's the goddess. It's not an acronym. That's the goddess of Jupiter. It's just amazing. It takes us 5 years to get to Jupiter. It's the largest solar-powered craft ever flown. We go into this orbital trajectory you can see on the right. And this beautiful, beautiful solar-powered spacecraft got us to Jupiter. We go into a very highly elliptical orbit on Jupiter because the radiation environment in Jupiter is 20 million times that of Earth. But we're still doing all this science. See, this is to scale. When you look at Jupiter, everybody wants to know about the red storm. One red storm, that's Earth to scale. Our entire planet fits into the red eye, the red storm on Jupiter. So just think about that. And that was taken by what we call the Jupiter cam. We have very high-tech instruments, but we put a camera up there, a cheap camera, and we said, hey world, what do you want to take? And so this is citizen science. We let kids, we let the public take pictures of Jupiter, and everyone wants to image that red storm. It's still raging, it's still the solar system's largest storm, and all of Earth, all of humanity would fit right in that one storm on Jupiter. So coming in a little closer into the, here we go. Where will we find life? We're going to Mars, and Mars has the chemistry, and we might find past life on Mars. We'll get to that in a minute. But there's moons in our solar system that are very ideal. They might harbor life. Why? Because they're ocean worlds. And when we look for life in the solar system, we say, follow the water. These are all water worlds. So you can go to Enceladus. This is to scale. Here's Spaceship Earth, of course, my favorite planet in the middle. Enceladus is very small. It's a moon of Saturn. That's the scale. But it's spewing hydrocarbons out of its south pole. So that's the chemistry. Sulfur, hydrogen, oxygen. You look at these places, say, wow, there could be life in the oceans of Enceladus. Europa. Europa is a moon of Jupiter. Jupiter now we know has over 100 moons. When we started the Juno mission, we knew about 9 moons of Jupiter. So these are the kind of discoveries we're making every day. Titan, Triton, Ganymede, Callisto. We need to go to all of them. They're all ocean worlds. Now the ice is kilometers thick, so we need to drill through that ice, and then we'll find the water, and perhaps we will actually find life. So that's the exploration of trying to find life, throughout our solar system. Why? To tell us more about life here on Earth. So we come down to Earth, our Moon-Mars system, close in. Mars is half the size of Earth, but it has fantastic volcanic mountains. Mount Everest? Nah, puny. Because we have Olympus Mons on Mars, right? If you go through the Grand Canyon in the US, is a beautiful, wonderful Grand Canyon, but I have Valles Marineris on Mars. It would stretch across the entire United States. They're going there to look for past life that might have existed on Mars. Earth and Mars are 4.5 billion years old each, and Mars lost its electromagnetism, its dynamo, 3.5 billion years ago. But we think it might have had life. It had water, and it might have harbored life. Today it's a very cold, dry planet, but we're there with our rover. And I'll show you some of our latest data. So from Mars to the moon, we're going back to the moon in order to get the technology that we need to Mars. And all of this has to have Earth applications to help humanity here. We have the MIT experiment on Mars today. It's called MOXIE. It's a Mars Oxygen In Situ Resource Experiment. What does that mean? As Norman said, we are living off the land. We go to the regolith. All successful exploration went to across the seas, went to Antarctica, and you had to learn to live off the land. We have a lot of regolith. We have a lot of basalt. So what we're doing with the 1% carbon dioxide Mars atmosphere, we're splitting off the carbon atoms, recombining the elemental oxygen, and we have oxygen. So it's the first time we've ever been on another planet. We're making oxygen. You might think it's for the people, to keep them alive, for my astronauts. No, that's secondary. Number one reason is for fuel. When we send the human mission to Mars, it would be wonderful to have our fuel depots already there on Mars for us for the return mission, because it will be a return mission. It's not ethical to go one way to Mars and leave people there. We need to bring them home. They want to come home to their families and friends and all their loved ones. So we're exploring Mars. We've been exploring Mars for 50 years.
First flight of a powered aircraft to another planet.
We can now say that human beings have flown a rotorcraft on another planet. Let's get on, get more flights. Congratulations.
Dare mighty things. That was our Jet Propulsion Lab. That's Mimi, one of my former students. And it's to dare the impossible things. So every day we do science on Mars today, and we look at our avatars. So you can't tell me I'm not on Mars. When I'm in my virtual reality, I'm looking 360 degrees around, and I can take pictures. Now the rover can actually take pictures, but again, we're searching for the evidence of past life. So the geologists will argue ad nauseum about take a picture here, take a picture here. They all look like rocks to me. I'm an engineer. But let me tell you, the scientists will say, if you only get one picture to take that one. So we beam you up literally, and we all are in virtual reality 360 to see that we can do, what science can I do on Mars today? So that's the current rover that we have on Mars. Again, we've been on Mars 50 years, learning and mapping and monitoring, looking for those evidence of life. The box in the bottom here, that's how big the MOXIE experiment, our oxygen making experiment. It's like a shoebox. It's just about this big. And I want to show you some sounds from Mars. We have a microphone. Always bring a camera and always bring a microphone on your space missions, because that's what people want. They want to hear it. They want to see it. So here's what the rover sounds like. We have a laser. We're tapping the rocks. Again, we're tapping the rocks with the laser to see if we can, what science we can come out. It's always windy on Mars. And here's an ocean sound that is an Earth sound, and then you're going to hear what it would sound like on Mars. Because that 1% carbon dioxide atmosphere of Mars is really low bases, and it filters out most of the sound. So here's what it would sound like from Earth to Mars. So the same recording, but on Mars. You can see it's very low in bass, and it filters out the sounds. And a meteor just hit Mars. We'll see if that's this last sound. I'm not sure if this sound file is, well, we might have to go on here. Can you help me with my slides? Pardon me, yeah. I think okay, we can go ahead and go to the moon. Oh.
First flight of a powered aircraft to another planet.
Can we go through these to the Marsans? Just, there we go, thank you. So these are my Apollo, my lunar bloopers. We have been to the moon. We went into these spacesuits. They didn't give a lot of mobility, but we kept the astronauts alive. This was Jack Schmitt, is the only scientist we ever sent to the moon. I think I might need some help forwarding here. Maybe I can get some help from the booth with going forward. There we go, thank you. There's a lot of videos. Not a lot of mobility, but again, you're in a pressurized shell. That suit is very heavy, it's not very mobile, but this was over 50 years ago. Amazing. So we kept all the astronauts alive and well and healthy, which was the point. And now we're going back. Sorry, my clicker is having some issues. This is the current spacesuit. We've been living on International Space Station. It's in low Earth orbit. That's only 400 kilometers up. It's 160 kilos. It's a pressurized shell, and it has to provide all of the life support to keep the astronauts alive. So we have kind of a radical different design. It's called the biosuit. We're shrink wrapping the astronauts because this is 20 kilos. And if I can have you move and be mobile and very flexible, then I think we have a better chance of getting the exploration done that we need to get done. So we kind of map and monitor, and we have some advanced materials that I'll show you in terms of we design, again, life support, but life support for these lunar and future Mars astronauts. So we've come up with some new materials. This is a video of a 3D knitted sleeve. It's going to apply 1/3 of an atmosphere, 30 kilopascals, to your arm to keep you alive. That's the pressure layer. You have to apply 1/3 of an atmosphere. It's your laser scanned. It's very conformal. You get your own suit. And invented some new sensing fibers that we put in there to measure what is the pressure, your kinematics, what are your motions. So those fibers are being integrated then into the 3D net suit. You see some black threads there. Those are carbon-doped polyethylene. That actually gives you some radiation protection. The first time ever we've thought about radiation protection going into actually a very lightweight suit. So multifunctional fabrics, sensing embedded, compression, you can tighten it up, as well as a lot of mobility. So we think that's the future of enabling exploration when we get back to the moon and Mars. Moon and Mars are actually pretty amazing environments. When you get to the moon, it's 1/6 gravity, so you're all superhuman. You can jump 6 to 7 times in height, and you can jump about 3 to 4 times your height when you get to Mars, which is 1/3 gravity. So we're all going to be, amazing, kind of like Olympic athletes when we get to the moon. And we want mobility, but probably not to just stay there in habitats. What about roving around the entire planetary surface? That's what we think might be coming. We will become interplanetary, but it's not option B. Again, we want to stay right here on the Earth. So these are some very early space settlements. I wanted to give credit to the 1970s of people living in low Earth orbit. This is what's coming next. A lot of people living just in low Earth orbit. It's only 400 kilometers up. Jerry O'Neill, these are the O'Neill cyclers and cylindrical living. And you might hear more about this from my colleagues and the other speakers. But I wanted to show these amazing images up there. There were the summer studies. Guy was part of these summer studies, and it was the futurists way back in the 70s saying, what would life be like? How are we going to live with thousands, tens of thousands? And now Jeff Bezos and Blue Origin Company is actually trying to turn this into a reality. From Jerry O'Neill's dreams to a lot of us in the 70s, 80s, and now 2020s to 2030s, we will really, I think, start having these become a reality. Okay, so I'm from the Media Lab. I want to dive down now, tell you a little bit, highlight a little bit about what we're doing at the Media Lab, down to Earth now from space, because all of our space research needs to have a dual application for Earth. At the Media Lab, I get to run this most exciting, magical lab, and it's because we put the artists with the designers, with the engineers and scientists, and we've teed up 5 areas that we think are the biggest challenges for humanity. Future Worlds is our climate and sustainability initiative. Life with AI, it has to be designed for people. AI is pervasive, but it has to augment the human experience. It has to uplift education, has to be responsible or it's not for us. Decentralized society, that's blockchain, that's security, that's privacy. You should own your data, and most importantly, it's about saving our democracy. Everyone has a vote. Everyone needs to vote in terms of our democratic institutions. Coming out of the pandemic, we teed up what happened to creativity? I don't know about you, but I didn't put any patents in. I wasn't creative during the pandemic. And so, especially for our kids. And then connected mind and body. What about mental health and wellness, as well as superhumans? We literally have humans and half robots at the lab. And so across the lab, we're working on all of these challenges, we think, that we can, in the next decade, in terms of what are transformative technologies, experiences, what can we do to really lift up design for human augmentation and human enhancement. Okay, so I want to just give you a little bit of a look into a little bit of some of the what we call future worlds, some of our climate sustainability work, and it really is imagining that world we want to live in, and then we take design and action for the world we want to live in. We take a space view, our Earth-observing satellites, looking down on Earth. We have Earth systems. We can look at the temperature, we can look at the water, we can look at agriculture, we can look at the ocean currents, and it really is monitoring. 50% of all climate variables can only be measured and monitored from space. I'll show you some temperature, world history of temperature, different than I showed this morning, to make sure you're still with me. From 1880 all the way to 2023. 2023 was the hottest year ever recorded. And so what do we do about that? You know, we want to make sure that people are not overwhelmed with the climate data. We want to make sure that you can think about, you have agency and you can actually take action every day to help. But this is just the temperature data of the Earth, and it is very hot. And you know, because in Europe you experienced every month was very, very hot last summer. We're measuring carbon dioxide, we're measuring methane. These are greenhouse gases trapped in the atmosphere. And if we change human behavior, we can change the direction and the temperature of not just our atmosphere, but our oceans as well. So these are all what I call the vital signs of Earth. It's Earth talking to us. We're measuring, monitoring. You remember this from 2017, the Iberian Peninsula. You can see the hurricanes coming up. You can see the dust off of the Sahara. And then Ophelia, the hurricane, came up. And those are the forest fires raging in Portugal and Spain that caused so much devastation. So it's, again, eyes on Earth, monitoring and mapping. And then we want to become local to get people out of harm's way. Our glaciers are melting. Just coming to the end of my time here, but these are all kind of the vital signs, what we're measuring and mapping from space, but particularly on Earth, our glaciers. This is showing the summer and the winter season, the ice on the sea and the ice on the land, just in the last 2 years. And then I want to end with, again, thinking about how we give people agency, how we look into the future with climate models. This is a slosh model for flooding. Pictures that are intuitive. We put artificial intelligence or machine learning put that together, and then we give you this, we image the future. There's pre-disaster, that's a lot of farmland and infrastructure, and then we've shown you a satellite image of the future of those flood. That flood is coming. You want to literally put it in your hand. It's called the climate pocket, so you can understand what's locally happening to my infrastructure, my home, get policymakers to get people out of harm's way. And then it has to be trustworthy, local, very educational. We put this all into virtual reality, and we let you be in the Earth mission control and take charge of all of these variables and serve them up. I brought some VR goggles so we can put you in the Earth mission control if you want after our talk. Kind of looks like this, but again, if people are in charge, if you have your hands on the dials, we think you'll make great decisions, and you work together, you know, in what we call the decision theater. So we'll give you a look at that, I think, if we have time after the discussions. Thank you very much for your time, all on behalf of Spaceship Earth and all of humanity, the 8 billion of us that live here, in terms of working collectively together through maybe spontaneous cooperation to get this right, to make it work for 100% of humanity.
Thank you, Dave. I wish we had longer. I feel so bad about having to encourage you to finish off, but we've got a lot to get through. And our next speaker is Xavier de Castellier, who is Global Head of Design at Hassel, based in London, an architect. And you're very welcome to join us on stage, Xavier.
Hey, thank you so much for having me here. It's a real honor. Let's get started. My name is Xavier. I'm head of design, but I also have, oops, there we go. I have a small team in London, and that's Hassel's innovation team. And what we'd like to do with that team is we like to work in extreme environments. And it can't get more extreme than space, of course. In the last 5 years, we worked on a range of projects. A 3D printed Mars habitat for NASA. We worked then with the Design Museum to build a complete mock-up of that for the Moving to Mars exhibition. We worked with Sierra Space to looking at a lower Earth orbit space station. And just this Friday, we launched a new project, and that's a lunar master plan for the European Space Agency. Now, what combines all these 4 projects together, what brings them together, is that we have a strong belief that we need to design for the astronauts, the people living in these spaces, to thrive and not just survive. I think we're beyond that. We need to thrive in space. I'm not going to talk about these projects really in detail or chronologically. What I'm going to do, I'm going to have the talk in three bits. First of all, lessons from space architects. Architects have been working in space for quite a while. I'm going to talk about 2 people, which I think are very inspirational for myself, for everybody else. Then, lessons from Earth. I think architecture and design are crucial in the development of human space exploration. And I'm going to talk about my projects by really using Earth design and thinking. And then we're going to take some of the thoughts that we've done, the learning from space, and bring it back to Earth. So we better get started. Lessons from space architects. First of all, one of my heroes, Galina Balachova. She was the only female architect working for the Soviet Space Agency. Well, actually, to my knowledge, she was the only architect working there. And she was crucial in the interior design of lots of the modules. This is an interior for an orbital Soyuz module. And I love how this looks very, very different. It looks almost domestic. Look at the detailing, at some of the wood veneers being used, even the little curtains. And, but she worked on stuff that flew as well, Mir Space Station. She was crucial in the color scheme that was decided to keep the orientation for the astronauts. Second person that I always look at, he got involved in Skylab. Skylab, really the first orbital station for NASA, and they brought in Raymond Loewy, the famous American industrial designer. And when he came in, lots of those engineers at NASA were a little bit baffled. They were like, what is this designer going to come and do? This is rocket science. This is serious stuff. What is he going to do? Choose the color? Well, he did choose the color, but he did a few other things. And two of those things that he did are on this image. First of all, he designed this table. You might think, okay, great, table, looks kind of cool, kind of tacky. But actually, in the original design, NASA engineers had given the astronauts a little tablet that was facing the wall where they could have their meal. So they weren't even facing each other. They couldn't even have a conversation. So they needed a designer to actually say, it's a good idea to have a table and face each other. Second thing, the window. The original design of Skylab, there was no window because there was a weakness in the structure. From a pure engineering perspective, you shouldn't have a window. But can you imagine being there in Skylab for weeks at a time and never being able to see Earth? Lessons from Earth. So I'm going to go to some of the projects. And first of all, International Space Station. I'm not sure about everybody here, but I personally wouldn't want to live in this space for too long. It's a little bit like you take the technical spaces, the core of a building, and you put it with the human spaces, and you mix it all up, and that's the space where you're supposed to live. We had the opportunity to work with Sierra Space. They collaborate with Blue Origin on their new space station, Orbital Reef. In particular, we worked with them on the life habitat and inflatable habitat. And what we did with them was kind of reorganizing the interior. So what we did was a very simple thing. We decided to put all the life support systems in a raised floor in the middle of the module. That way we could put all the messy stuff away and hopefully create spaces that are simpler and much more enjoyable to live for our astronauts. I've got some more critique on current space stations. This is the Columbus module in the ISS. This is a very typical module that we will see in the International Space Station, where you have on the left-hand side and the right-hand side, you have science racks, storage on the top, storage on the bottom. Now, interestingly enough, when an astronaut does stuff there in the ISS, they would just set up an experiment on one of the racks and then probably move away. This means that the ISS is actually quite large and it's full of corridors. Couldn't we, from a pure architectural perspective, do something better, more optimized space? And I actually went here, mobile shelving racks. Why don't we move the racks around? So for our design of our Mars habitat, that's exactly what we did. We designed racks that are movable. So if an astronaut needs to do some work, he can actually go in, open it up, do the experiment, and close it back. And that works for the lab, but it also works for the greenhouse. So much more efficient use of space. Not a technological solution, but just a pure spatial architectural solution. This is the project that our latest project for European Space Agency. We just launched it this Friday. It's a much larger project with many, many modules that are connected. The problem with a system like this is that if I want to go from point A to point B on the base, I kind of have to start walking through all the other spaces. It's like going from one building on the street to the one down the road and going through each of the buildings. Because we don't really have streets, we can't just walk outside on the moon. So we got inspired by this, skywalks in Minnesota. Because it's so cold there, people always stay inside and be able to connect to the different buildings on another level. So that's what we did. In our project, you kind of just see it there. We have these kind of connections now that will run on top of our base that let our astronauts to go from one point of the base to another point much, much quicker. So these are kind of streets on the moon. This is our Mars habitat. Again, we have these kind of shell structures here that protect our astronauts. The 3D printed reglet that we would use would not have much tension. It would have to be under compression. For that, we looked at people like Gaudi, using hanging chain models, but designing structures that are under compression only. We don't do this anymore. We do it very digital at the moment. So we worked with Callaghan engineers in designing these shell structures that we know are only under compression only. So we're able to kind of design with this Martian regolith or lunar regolith. Now, The way we did it for our Mars project was we were thinking, let's use small robotics to do this and print it layer by layer. Now, we came back from that idea a little bit because we thought it might be quite complex to do this in situ 3D printing on another planet. So we've been thinking there might be different ways to do it. You know, there's other ideas of doing shell structures. This is a beautiful shell structure by the Block Research Group in the Venice Biennale. The problem with something like this is it needs high precision engineering, it needs high precision fabrication of elements and high precision assembly of elements. We need something much rougher and easier, an easy solution for space, we think. And we're thinking of this. A very simple system of really almost dropping these blocks. We call them tetrapods. And to create a structure. Now you might have seen this before. Yes, we had them in coastal barriers, right, to protect our coasts. But couldn't we start building with these? And this is our idea. So we start off with a foundation of these tetrapods because there will be quite a lot of forces reaching into the ground. And once we've done this, we will create in the middle what we call an inflatable support structure. Now we have a bit of a crazy idea. We thought, are we going to have a crane placing these? Well, maybe not. Let's use this idea that we have 1/6 of gravity and play with it. Maybe we can throw them. Be easier to throw, 1/6 of gravity, easy to throw, and the impact they will make when they drop down will also be less. So we're going to actually test this out. I'm printing 4,000 of these at the moment. We work with the University of Toronto and a robotic system there that will throw 4,000 of these on top of an inflatable in the next couple of months. And hopefully, after we've done that, we can take the inflatable back out of it and it creates this shell structure. So here you see our coastal barrier system becomes now a protection system for radiation on the moon. Now, we need to be protected from radiation, but we also love a view out. This is the cupola, the place all the astronauts want to be on the ISS. But it also has a protection system. If you look outside, it has these flaps that can close it for debris coming in or for radiation. Now, this is a very mechanical system. I thought there must be an architectural way to do this out there. And we did it. We thought of a courtyard. Isn't a courtyard a way to protect ourselves from the sun, from direct sunlight, but at the same time bring in indirect sunlight and still get views across a courtyard? So we just designed a very simple system, an architectural system again, to deal with the radiation and still have views across in our habitat. Now, going to another planet or going to the moon is always expensive. So every kilogram counts. So what we need to do is, I would say, pack compact and light. Now, systems that are light and compact, inflatables. And we got inspired by this structure. It's a tensarity structure. It's a way to create a beam out of an inflatable. There's a beautiful car park in Montreux in Switzerland that's designed. Like, there's a very few buildings designed with this system because you need a permanently inflatable bladder. On the top, you get a compression system, and on the bottom, a tension, which could be just be cables. And that's what we did for our habitat, our main habitat module on our ESA master plan. We get a system that is able to kind of lift itself from the regolith, because you don't want to be in contact with the regolith. It's very sharp, and it's also an inflatable. Now that became our base module. It's 23 meters long, it's 10 meters deep. And that base module gives us an opportunity to house 6 astronauts. Now, if we have a growing community on the moon, and the plan that we did now is from 6 astronauts to 144 astronauts, we will need to be able to change the space and grow it with more modules. Now, for us, this became the right module, and we're able to kind of fit this out now with kitchens, with restaurants, with labs, with greenhouses, and so forth. So for us, this is almost our city block, right, in our master plan, and we're able to fit it out in different ways over the future. And here you see these kind of 4 of them connected with each other. Okay, lessons from space. Let's go back to Earth now. When I was working on the 3D printing Mars habitat project, these were the rovers that we designed. Some of them are actually inspired by NASA research. And halfway through the project, I got this visualization back from our visualizer. She did a fantastic job, I thought, because it really showed how I wanted to have more of a homey feel to that living space on Mars. But there was a problem, I thought. Well, that was here in the corner. The visualizer thought, well, all these robots have just done their job. Let's just park them somewhere. So, to my horror, I just created the first boneyard in space. I just arrived and I made a mess already. We need to think differently. When we go to another planet, everything we bring has to be useful, but not once, for many times over and reused. So, back to the drawing board, we redesigned the robots. We made the robots much more modular, as almost a Lego system that it could connect and have different functionalities. From outside even to inside, here our robot is helping out fixing another one in the workshop with our astronaut. And we started to think. We thought, we should think of everything like this. Everything that's on the base should be, and everything that we bring, we need to have a second life. Even this is the Perseverance rover landing on Mars with a landing chute. It's only used once, the parachute. Why shouldn't we keep on using it? So this little fun thing, we start working with Chris Rayburn, a designer in London who does exactly that. He designs clothes from parachutes. And so we had him kind of clothing our astronauts for the renderings. I'm actually wearing, the suit I'm wearing today is actually made out of old parachutes as well. So, and making these renders, we started to put little clues in on how we could live a different life on a different planet. You know, all the wood that you see, we wanted to have tactile materials in there. The wood is actually bamboo veneer, grown on the moon. The cushions in there, they're mycelium covers, mycelium leather, grown on the moon. So we have to start behaving very, very differently. This is our bar on the moon. 144 people. I think we're going to have a bar on the moon. But it also gives a few clues. You see, I've kind of like took some parts of old jet engines. We made a little table, as I might have ripped out the seat of an Apollo rover to use in my bar. And we kind of started having these seats. So they're not very light and compact, these. That is because those would be 3D printed on the moon or Mars. From packaging material, from food packaging. So all the waste we could use and then 3D print it into furniture. In this project we worked together with Manuel from Nagami, who I hope is here. And after this project we took it one step further. Because we came here and did a robotics atelier in the foundation. And we worked with a group of students where we said, yes, we can do furniture with recycled plastics, but could we start to think about building components? Could we reuse our plastics in buildings as well and use it through 3D printing? It's a fantastic week, and we thought we're not going to stop. So we continued. We found a client that was interested in this whole idea of 3D printing buildings. We designed this pod, a tiny, tiny building, a meeting space for cold climate. But because it's 3D printable, we're able to kind of like change the geometry of it so it actually can be used in hotter climates as well. This is the version for Senegal. And we're printing it only an hour outside here in Avila. All the parts are being printed. We're assembling it right now. It has different skins for different climates, as you can see that here. Now, for me, it was really a kind of working on these space projects, revelation that I needed to work more sustainable, and we need to use more local materials in our architecture. On Mars, I was using regolith, local materials to build. We should do that on Earth as well. This is another extreme environment. This is Bidi Bidi. It's the world's second largest refugee settlement. It's in northern Uganda. and has 270,000 refugees from southern Sudan. We worked on a project there to do the Bidi Art and Music Center. This is the first ever cultural building in the refugee settlement. 270,000 people, and there is no other cultural centers. I'm from a city that's the same size as Bidi. I'm from Ghent in Belgium, 270,000 people. We have operas, theaters, design museums. There's nothing there. This is the first one. And we wanted to build as sustainable as possible as well, although it is in a really extreme environment. So we're working with CEB, compressed earth bricks. We're working with the local community there who are part of building the building. Of course, with a professional contractor as well. And I was going to show a video, but I just got this picture. And this is how the building opened just a couple of weeks ago. This is just a snapshot I had. We don't have professional pictures yet of this project, using mainly local material and not robots, but local refugees. Thank you.
Thank you, Xavier. That was great. Thank you. And our final speaker is Mark Guberman. Mark is a senior partner at Foster & Partners based in LA, California.
Good evening. What an exciting day. I'm the last speaker, so I'll try to be brief, but I can't help myself sometimes. But really, what a beautiful day. An institute was formed, great ideas were shared that have parallels and differences, and I hope that someone can get some debate out of us in a little bit, because I think it would be really welcomed for the audience. But first, I'd like to take you through a little bit of, it's a three-part story. I want to go through the origins, then the pivot, and then our latest thinking of off-Earth space architecture at Foster & Partners. So let's look at the Earth for a moment. You could say that the evolution on Earth was nature first, humans second, the habitats third, and the robotics last. Now, let's fast forward a second to the Moon or Mars. Great distances from the Earth, maybe 3 days, depending on when you leave and what propulsion system you use for the Moon, and much longer, 8 to 9 months, if you're going to Mars. But what might be the evolution sequence there? Could it be the inverse? I'm just proposing this. Robots, followed by dwellings, followed by people, followed by nature if we're lucky. But there's a missing ingredient here. And I'm going to talk about this in a little bit, which is the robots designed by us are infused with natural ideas, biomimicry, things that we have learned here on Earth. So first, let's begin with the origins. We began in 2005. We asked this simple question. Can 3D printing aid or facilitate the off-Earth exploration project? And we had a resounding answer. It was a unanimous answer called yes. So if you go back to around the mid-2000s, we first, like a lot of people out there, we got 3D printers to help to illustrate and communicate design ideas. We quickly moved beyond that to not only a design communication tool, but to aid in the design process itself. And once we got to the third level, we began to take common building materials, construction materials like concrete or clay, or even metal, where you could have multiple robots printing in unison, dancing in unison, in an additive but also a subtractive way to create structures and shells. But where do we go from there? We found and discovered, in the early 2000s that the off-Earth project, independent of what it stands for, but because of its DNA, because of the constraints of what it's like to go off Earth, the radiation, the change in atmosphere, the different gravity, the micrometeorites that we've all been talking about, it's so challenging out there that maybe if we put these constraints to work, they will yield productive R&D solutions. And so we see the off-Earth project as alone a great place to apply this R&D thinking, and it's very productive, as you'll see. So we talked a little bit about these earlier. I'm going to move through them rather quickly. 2012 was one of our first projects, lunar projects with ESA. There were 4 main components where a piece of capital equipment, a very intensive, heavy, and expensive piece of capital equipment from the Earth is shipped to the moon. That's number 1. It has life support, and it also has your airlocks. Number 2 is an inflatable rib structure that comes lightweight and it blows up, and it's in a geometry and a shape that's very conducive to high pressures. Number 3 is where the 3D printing begins. We add the regolith to protect and create a shell around the whole enclosure, and number 4 is the inside. But look at this Cape vulture for a second. Birds, majestic, they inspired us to fly. And if we zoom in to their wings and we look at the molecular and muscular and skeleton structure of their wings, it might lend clues to how we survived off Earth. And like Norman talked about earlier, we zoomed into this, and the bone structure has 30% less mass, but it has the same amount of strength and resiliency as what would be a solid object. And so we use this not only in our digital desktop analysis, but we also were printing one-to-one details at the same time, like you see here on the right. Now let's fast forward 3 years. Let's change our client. Our client here is NASA. This is a competition with NASA, so we're not working with them yet. We're showing them our design skills for the hope one day of working with them, which I'll get to in a second. So on this project, think about it for a second. Mars is very different from the moon. Its distance, 8 to 9 months versus 2 to 3 days. It's over 200 times the distance, which means that driving a robot on Earth has a 20-minute average latency. You can't drive them by humans. You have to be self-autonomous driving. So like Xavier pointed out, we got really into swarm robotics, and what we loved about looking at the birds, in this case not a singular bird, but a collective mass of birds, is that they have in their DNA all these sequences, all these codes, so that if a bird fails or gets injured, you go off to the side and you help it. But because there's so many birds and there's so many swarms out there, the mission does not end just because one robot fails. So here, it began with landing the robots first, and we call it the multi-robot system because these robots did many things. They were lightweight, let's call it one blue parachute. In the second step, we were landing the lunar habitats themselves. They were compact, origami-like elements that were heavier, so they required 3 balloons, in this case, the orange tone. They land, they find each other, 3 of them cluster together. They begin to unfold and expand and inflate. They come together, and then the robots around it add the regolith. One of the things that was very interesting, this is 2015, we didn't stop with the structure. We went into the interiors. We even went into some of the early ideas for clothing, early ideas for greenery inside of the shells, and really looking at how these different ideas and spaces could connect and work together. Now I want to talk about the pivot. The pivot came in the late 2010s when we really started to question some of our initial ideas. And the pivot came by request, in a way, of NASA. NASA asked the community of designers and space architects in the world in 2017, can you design a new material for use on Mars that uses Martian regolith to 93% of the capacity? So whatever we showed them had to be 93% Martian regolith, which for all intents and purposes is very much like basalt, one of the rocks that we have here on Earth. So we, along with our engineering material science partners, we recreated a new material. And then they were very prescriptive. This was not a design experiment. This was a technical and engineering experiment. They gave us a dome enclosure and they said, we want you to print it as fast as you can with as little amount of material as you can. And then we want to not only time the printing, but we want to start to load it up. So we all went to Peoria, Illinois, about an hour outside of Chicago, at the Caterpillar headquarters, and like a live NBA or football match in Europe, they had large screens where everyone's dome was getting compressed by giant machines. And fortunately for us, we beat Penn State, who came in second, and we came in first. We withstood about 3x the forces of what they did. So it's not just about the material science, it's about the structural engineering, and it's about the sequencing of the 3D printing that in the end was our innovation that yielded a win. What was most incredible about that is that led to this project and one more that I'm going to talk about. These were no longer competitions for NASA, they were collaborations with NASA. And I think one of the interesting things about it is when you get hired by NASA, and I'm sure it's similar with ESA and some others out there, they give themselves homework. They sit at the table with you. They are part of the design team. Yes, They write the grant and hold the project management and facilitate the live meetings. But they are a design partner. It's an engaged client. So this project was pivotal for us as Foster and Partners because we really started to question, what if we land here, but a month later we find water, or we find that there's more daylight over there? Are we going to abandon the habitat that we just built? Or can we reuse it? Can we deconstruct it? Can we pick it up? And can we go over there? And so we really started to decouple the shell from the habitats. And you can see that in this case, or even more closely in this model, where we build the shell first, using what we call space bricks, and then we use a binder to clad the space bricks together. But the space bricks are not wasted. They're not one-time use. They can be disassembled and reused. And then we have the habitats going into it, where some of the spaces can be buried, like the bedrooms, and some of the spaces, like the greenhouses that you see in the orange-clad membrane out there, can be further out towards the sunlight. And again, we were inspired by, swarm robotics. In this case, it was termites instead of, the birds. But what was fascinating about this was it wasn't just the sequencing of it, it was the software engineering and the hardware engineering and the coding of it. And so we took these ideas that you see here in this film, and we started to run it through the simulator, through the machines. We started to hold live demonstration events for not only other space architects and engineers, but also for the next generation, students and children, trying to explain to them what we're doing. We saw this as kind of a happening, an event where everyone could learn, and it's not just drawing a rendering, but it's proving it in real space. Now I want to change to go to the habitat for a second, and less about the exterior, but more about the interior. Basically, right now, the NASA ISRU project, which is in situ resource utilization, it's a very commonly used term in the space architecture industry, is divided into 3 categories. The habitat and infrastructure, which have been ongoing projects since the early 2000s, and what they call outfitting. Outfitting is one of the newest ingredients and chapters of their ISRU project. It stands for everything inside of the habitat. And so we were lucky enough in 2022 to work with Branch Technology. They're a 3D printing specialist based in Chattanooga, Tennessee, that you see here on the left, and have the opportunity to do the first outfitting project with NASA. The reason I put these 2 slides up is the project was extremely technical again, but this time it wasn't just about construction and material science. It was also about human and environmental science as well. So here, we got inspired by biomimicry again, but instead of the birds, instead of termites, it was barnacles. Barnacles secrete a natural protein that over time, as you know, if you've been out to sea or underneath some of these piers, are extremely strong. So we were looking for what could the barnacle-like binder be off Earth? What could the biomaterial be? And we, working with Dr. David Loftus of NASA Ames and Dr. Michael Lepek of Stanford, we collaborated and invented a new material we called BSC. BSC is a biologically bound soil composite. It has 3 ingredients: the regolith, the water, and the biomaterial, the protein binder. In this case, we use bovine plasma as the protein because we believe just bringing a little bit of this ingredient, which is abundant on Earth, off Earth, would be enough to, the first thing you would build is not the habitat for the humans, it would be a synthetic biology lab where you can recreate more of the bovine plasma protein when you're out there. These are some of our first demonstration samples for NASA that actually worked. Then at the same time we were doing the construction and material science kind of thinking, we were also coming back to the human. We were taking very core principles. If you've ever heard of the term alesthesia, what it means is that to stay energized and sustainable as a human being and focused and healthy, long term, you can't have a constant stasis of temperature, of air movement, or even of stimulation. That for pleasure and to be alert and to be happy, you need a dynamic environment. So we were lucky enough to be put in touch with a few of the habitat crews from the Mars 500 mission. This was a space analogy mission that was done in 2010 through 2011. It was Russian-led. And what it was 6 different crew members were put in a roughly 200 square meter or 2,000 square foot space for 520 days. It was to simulate the trip to Mars, 20 days on Mars, and then the trip back. And they had all the different areas of life that you would need, from eating and sleeping and working out and science, of course. We got connected with Roman Charles. He's a Frenchman who was part of the Russian mission. He was selected. We spent hours interviewing him, talking to him, and he would describe these moments of near failure where he would dream of the sensation of water, or the sound of leaves, or the feeling of being held or submerged. And they weren't hallucinations, they were just longings for what could be next. One of the most critical things he told us was anything that could break the monotony of life in that habitat was a good thing. And then something happened. 3/4 of the way through, they lost power. And it wasn't by design. The Russians didn't shut off the switch. It happened naturally. And for those 24 hours, they said it reset their bodies. It reset their minds. So something horrible, like losing power, turned out to be the most exciting moment of the study. And this is actually one of the images he shared with us. It's an incredible image when the power was out. The other thing that we're learning is that it's not just about diversity of the climate and the temperature and the wind or the sun. It's also about colors. So we looked closely at the different minerals and objects on the lunar surface. We actually started to print our BSC tiles using those tones. These are actually tiles that are printed by us. And again, Galina Balashova, as you just heard from Xavier, was the queen and the leader of this thinking 60 years ago. So what you're seeing here, and we have not shown this ever, this is the actual first lunar outfitting project that we did with NASA. These are the wall systems and the components. Obviously, we integrated all of the systems into it, whether it was the lighting or the different connections for data. We did put an artificial skylight in it for the moment to test how that could work. And then, of course, it was about a kit of parts, plug and play. So could it be holders for plants, or could it be a desk, or could it be a bed? We actually have a one-to-one mock-up of this built right now in Branch Technology Studio in Chattanooga, Tennessee, and we're looking to bring it to one of the science museums, either in California or the East Coast sometime soon. I want to pause here for a moment because NASA, the relationship we have with them today, could not have been possible maybe 60 years ago, right? So back then and today, they have amazing skills. They can do Earth observation, astrophysics, planetary and Earth science. But there are some things they don't do, and they've recognized that. And now they've opened these doors to combine their ecosystem with our ecosystem and Branch's ecosystem, and also with Stanford's ecosystem. So one of the ideas we were also writing as we wrote this project of material science and construction capabilities, and also human psychology, was that all these organizations have to come together to really go further and advance the space movement than any one of us could have done alone. So now on to the current thoughts. This is a different map than Deva showed. This is showing 60 years ago how circuitous the planetary exploration program has been. In other words, 60 years ago, no one could have drawn this map. This map is a byproduct of people staying true to their minds and their hearts, and also the mission at hand. So the question is, what is the next 60 years? So if you just compare for a second the image leaving the Earth, going into Earth's orbit on the left in the 1960s, and the image leaving the Moon's orbit on the right, look at the massive different scales and sizes of machinery. Look at the different explosions that are taking place. Why is this? There's a different gravity pull. There's a different amount of energy holding you into the Earth versus holding you onto the Moon. We've talked about on the Moon you have 1/6 the gravity that you have on the Earth. But when you translate that into the forces needed, you need 1/24 less energy to get into the Moon's orbit than you do the Earth's orbit. And so the Moon for us becomes this kind of potential hub. It's to get there, but then it's to use that Moon as a base for extraplanetary exploration. And just to get back into the scale of things, you know, we're talking a lot recently about Australia. You could fit the Moon inside of Australia. It could be circumscribed by Australia. So it's small, but it might hold the clue for all extraplanetary exploration. What I'm so excited about today is that certain things, like the image you see on the screen, and even this 3D print that I have made here to pass around, we've always been able to get some definition and fidelity of the Moon's surface, but every day, even now, 2 days after this was printed, we could even do a better job. So we know exactly where we want to go. We want to go to the Shackleton crater, but can we be even more specific? Yes. Where you have location of interest A, that's the ridge. It's flatter, it's broader, it's less risky than being at the crater's edge. But the crater's edge may have more daylight. It has an opportunity to look down into the crater or to look across over the other end of the crater. So what I would say about our current thinking is we're moving into an era of hyper-specificity. Before it used to be, we'll just land somewhere and then we'll take it from there. But now we know exactly where we want to land. And what's really interesting, it's a kind of a sometimes it's a little hard to read in this slide, but we're overlaying in this slide what it actually looks like in terms of the daylight on this specific space on the Moon for the average day. And so we were not able to do that kind of collapsing of the data, let's call it 1 or 2 years ago. This is another view, and by the way, we're not artificially lighting this model. This is the actual illumination of the sun at a certain point in time. So you can see that the two locations that we're interested in are illuminated, and it's not by accident, it's by design. The other thing that I want to point out is we're also starting to get hyper-specific, not only about the where, but about the when. So when we talk about the Artemis mission or how we might contribute to it, we talk about, is it the first stage, kind of foundational habitat that might occur around 2030, or is it the later stage long-term habitats that could happen around 2050? And we have a very different sort of debate going on in our company right now about potentially there's a different solution for each. Could the first be more of a light touch? Could it be more like an airstream or a tent? Could it be something which is extremely flexible and mobile and moves on? And then once we find the area long-term where we want to call our base and our settlement or our city, then we have something that's much more monumental, much more heavy, much less dynamic. I just want to close by looking back. If you look back to the Paleolithic nomads, okay, 17,000 years ago, we have these artistic drawings on the caves in France that depict why nomadic behavior existed. They had to move season to season to find cover and shelter and food. If you go back about 5,200 years to these islands off the coast of Scotland, you can really get early ideas about in situ resource utilization. This is them working with their rocks, and by the way, these have withstood the test of time. So these are still standing to this day. Or even going back just a little bit to the Inuit people that you have in Canada. They were experts in being a migratory social community that had very little waste. So everything was multi-purpose, was reused. Even the prey that they slaughtered to eat, they would dress themselves, obviously, in those coats. And I just want to close with this kind of really interesting study that we've been doing recently about methods of exploratory conduct. So what could we learn from people that have been explorers before us, right? Because we're not the first explorers. We come in a lineage of explorers. And we've been looking really closely into the Norwegians and obviously the South Pole expedition in 1912, where they worked with wolves and dogs that knew the land. They trained in high altitude climates. They even wrapped themselves in porous and breathable clothing made from the animals themselves. And obviously they were the victors. So my closing thought, I won't go into this quote because others have already, but I'll say this. Overview Effect 2.0 is on its way. When it's coming, none of us know. But there's a great chance that the individuals in this room, whether they're the council members or directors of the new Norman Foster Institute, whether they're the faculty or whether they're the students or the children, if there are any in the audience, I bet you some of the people in this room will be responsible for Overview 2.0. Thank you.
Thank you, Mark, and welcome back to the stage, Xavier and Deva. Thank you for those comments. Let me preface what I'm going to say. I'm a child of Apollo. I love this stuff, but I'm here for the cities, right? I mean, you've each made the case with great enthusiasm that there are products, there is architecture that has benefits on Earth, that by thinking about it off Earth, we can find benefits on Earth. But we seem so far from anything like a real city, the subject of this institute, that surely we can't wait, can we? The Earth's needs are too urgent. Isn't the real benefit of your work on cities the thinking rather than the doing?
I'm going to go first. I'll start. So we have time to go into it, but when you think of sewage, when you think of these habitats, first and foremost, you think of life support systems. When you think of closed-loop life support systems, now what do our cities need? First, we need clean water. The world needs clean water. And what we learn from space is how to close the loop. So to be very efficient. So we have to close the air loops. You know, they're totally regenerative. And the water, and I'm talking the water loop, is completely closed. So anything you drink today, you excrete, guess what? You're going to use that tomorrow. So these are just a couple examples of extreme technology, life support systems that are very, very beneficial for the cities of the future. The cities of the future that are going to probably self-propelled, self-generated, and they can use, again, this is really a good example of dual-use technology, I think.
Yeah.
We will be on the moon this year, actually, coming up.
But when are we going to have a
Put a camera up there. So I'll take a picture of Shackleton Crater, because we're going to fly a swarm of robots and a stereo camera.
Wonderful.
But Xavier, when is your moon master plan? And by the way, I'm waiting for the Mars to plan that one of you is going to create. Sorry. When is that happening?
Okay. I'm going to disagree with you here a little bit because I don't think we need full cities, right? It's going to be a long, long time before we need that. When we design for these places, one thing I often do is look at Antarctica and look at the bases that we have there. Again, it's for a few hundred people most of the time. They're communities, right? Maybe villages, not cities yet, yeah. I think. And for me, that's really where we should go, right? Because I always ask the question, we don't live on Antarctica, do we? Right? There's no point in bringing up your children there, is it? Nobody would want to, because the environment is so harsh. So should we go to all these places for exploration, for science, for industry, for tourism? Probably yes. But should we have cities of hundreds and thousands and millions of people? I'm not sure yet.
What's your view, Mark?
My view is, of course, it's going to be a fertile ground for research and science, but I also think it's a fertile ground for us humans to satisfy our innate hunger for exploration. I think we're all wired explorers. It's part of our DNA. I think if you look back to really early books or film, you know, the idea of going to new ground is pervasive. I mean, why is it that children, before they even know what the word means, they want to dress up for Halloween as an astronaut? It's a weird thing, right? Because there's this kind of appetite for new boundaries, and I think that's what's exciting. We will push ourselves to the limit, and we'll do that on Earth. Hopefully, we'll explore mountains and the deep sea more. The deep sea is another kind of rich area that we're not exploring as much, maybe because the business case for mining the deep sea isn't the business case yet that people have made about off-Earth mining. But I think there are fertile territories for that exploration, not only off-Earth, but also on Earth as well.
And how do we, I mean, do we need a little humility here, that if we think about human exploration on Earth, colonization, European colonization, it hasn't exactly been rich in success. It's been fraught with conflict. Dava, you held out with your exoplanets the possibility we might travel to, at some point, to these places in the future and find new forms of life. What are the risks of the damage that might be done by simply interacting? Are those considerations that each of you make in your work?
Well, we make the governments take those into consideration. So NASA has a forward contamination as well as backward contamination. So let's just take Mars, for example. When we go to Mars, we have to make sure not to contaminate it. And there are very strict policies and rules. And at the UN level, we work on the peaceful use of outer space as well. And then backward contamination, we have OSIRIS-REx, we have asteroid. It just got opened up yesterday. So we have, regolith, if you will, from asteroid Bennu is being analyzed, but under very, strict quarantine. So we really do pay attention to forward contamination, backward contamination.
Yeah, I mean, are we exploring for the sake of it? Why are people thinking about these cities? Is it because, they're there? You explore because it's there. Why do you climb the mountain? Are they thinking of these cities because we're giving up on Earth and we need the plan B, the Elon approach? Or are we genuinely wanting to explore space and settle in order to somehow benefit this planet? Where are you in this, Xavier? For the sake of it?
Personally, I know Elon wants has this idea that I think it's in the next 100 years, 1 million people on Mars. So if there's something terribly happens here on Earth, we can just reset human civilization. I don't think that's feasible, to be really honest. I'm not a believer in that. I do believe in exploration, and we do that because we're human beings. We've always done it, and we always keep on doing that. Hopefully we can do that in a bit more of an intelligent way. And you know, what David talking about, being very careful about contamination and all that. I hope we can kind of do it in that spirit. But do we need a reset? No, I think we can work on Earth and learn really from how harsh these environments are, and I've showed in my presentation, and how we need to be careful with our resources and use and reuse and recycle and upcycle continuously. We need to start to rethinking in completely redesigning in different ways. Just to explain this a little bit, I think the way we procure architecture is not set on us being able to reuse materials. We work on a very small project in South London at the moment, and as a test case, where we're only going to build with non-virgin material. That's actually very hard to do, because the process of designing, tendering for a project, going to a contractor, doesn't line up with that thinking. So we need to completely start rewiring how we design, I think, to be able to kind of embed this idea of being able to work with, for example, design with 100% non-virgin materials.
Mark, can I ask you about,
yes.
let's move it on. Can I ask you about gravity? I mean, yes. I get excited when I think about, what is it, the moon is
1/6.
1/6.
Moon's 1/6,
and Mars is
3/8.
2/5.
3/8.
Okay.
3/8. 1/3.
And you showed David the video of people jumping. I mean, that looks amazing. I mean, going beyond Apollo, falling over and clumping about in these heavy suits, to actually leaping. And I was thinking about what happened on Earth in the early 20th century, late 19th, early 20th century, when we defied gravity by the creation Otis and the elevator, and I think the revolving door to deal with the pressures that are created in tall buildings. Are you thinking as architects about what's the next form of vertical circulation that we don't yet have?
Well, we kind of embedded in our project for ESA already. It's a few things, right? Moving horizontally, right? It will be quite weird, because you'll have to almost jump, right? If you see on the moon. So in our skyways that we have in our projects, what we've done, we've had these handrails that people almost kind of use their arms as well to move forward. The other thing we thought, well, moving up and down, right? Stairs. Well, we don't suddenly get very long leverage or long legs. So our steps are actually the same to go upwards. But then we thought going down, well, if you jump down in 1/6, that's easy to do. So going down, you can jump. Going up, we still use stairs. So we kind of started to embed all these things. Ceilings are a bit taller as well. So little adjustments that we make in that design.
And Mark, if we could build these cities, would you go hyper tall? Everything seems rather sort of low and cavey at the moment, but...
No, I think there's a case for density, and obviously those of us who were benefiting from the earlier conversations today, we can go into that in detail. But just to go back to something, because I think you went through too and you missed me, but could it be a good conclusion, and just for everyone's sake, plan A in the space world is the Earth is doomed, let's get out now. Plan B is, at some point, if it's doomed, we have a backup. And I think a lot of us here are saying it's kind of plan C. It's this world for R&D, and let it take its place. Let's stay serious, let's stay focused, but we don't need it, right? We have to correct what's going on here. And I think what I just realized from today's discussion is it actually puts more emphasis on all of the great different policies and social drivers and design drivers that we talked about this morning. Yes. It's like we can't use the off-Earth program as a relief valve to just not fix the situation we started, right? So it puts more attention on Earth, and I think we can all share different anecdotes about what we think are the most productive lessons learned. Xavier even organized his speech around that. But I think that's the way we should use the off-Earth project right now, as well as trying to go into the exoplanets and see if there was a previous existence on Mars, for example, why did that end? How can we not be Mars 2.0? I mean, that's powerful. But we have to get to that stage first to move beyond conjecture and supposition into the data.
I was offering you the 5-kilometre tower there, but you've chosen to give a decent answer instead. We have some microphones, and we've got a few minutes for any questions that may be here in the audience this evening. And I really encourage you to put your hand up if you'd like to do that. Just while you're thinking about what you might want to say, Dave, I've got a thought about if we really were to travel far. If we were really to go and visit, let's say leave the solar system, travel great distance, for whatever purpose, just to be on the ark, we lose our contact with Earth's technological progression. We were hearing earlier about in the last decade, 2 decades, the internet, the mobile phone, social media for all of it. You have technological lock-in because you're not being fed with the updates if you're so far away. Is that something that is thought of?
Well, you don't need to go out to the solar system, you just need to go to Mars. You get to Mars, again, we have, as mentioned, a 20-minute delay, so you have to be completely autonomous. And also you lose vision. The Earth is just a little pinpoint, and so it's going to really affect the psyche as well. When you get to the moon and you see that beautiful Earthrise, and even when you're in low Earth orbit, every 45 minutes we see a sunset and a sunrise. It's 90 minutes, in orbit. You get to the moon, you see that beautiful Earth. When you get to Mars, now you've already lost contact with your home, if you will. So you have to have you have to be completely autonomous. So you do have to think about different systems, different technologies to be able to survive completely autonomously. So with humans and the crew needs to be really able to work autonomously. I want to mention one other thing that's relevant to design, especially for the moon, is lava tubes. Lava tubes haven't come up yet. And it's really important. We've been talking about structures and living, and again, if you explore and you live off the land, probably we're going to have a lot of capability underground or in tunnels and lava tubes, and then they have to be designed because that's the natural structure of the moon, and the Mars is volcanic as well. And so these have huge benefits to be put into the design equation, if you will.
I'm looking for a hand, and please, this might be your final, because time's against us, opportunity if you wish. But in the meantime, Xavier, you mentioned something in conversation a couple of days ago. Could you tell us what happens if you die on Mars?
I knew you were going to ask me that. So when we sat down for the brief of our last project for ESA, one of the officers at ESA asked us that question. He said, you need to start looking at what happens when people die on the moon. We have a big community. And I was like, I didn't really think of it. And he said, well, there's very little carbon on the moon. Just having your human body is full of carbon. You better start reusing that as well. So, yeah.
We have to...
So it begs the obvious question, for what?
Plants, growth, that needs carbon. Farming,
Yeah. Who's got a question? We have a question here, sir.
My question is, why space architects and space architecture are so obsessed on 3D printing? We have 0 successful project of 3D printed buildings on Earth, and try to imagine how that specific process for specific purposes to be used on other planets with huge 3D printer prepared material. So drawbacks of this technology to be used, but that is on 99% of project I found on the internet.
Mark, would you like to pick this up? I think we've got why are so...
Yeah, I think what he's asking for is
3D printing.
Why all the obsession with 3D printing? And I think we didn't really talk about it, and it's a term that used to be called pre-colonization. I think now people are calling it pre-human habitation, but it's too dangerous for us to go first. The amount of time we'd have to be there and wait to get protection and set up the habitat or the lab or whatever it is we want to build first. So the idea of using autonomous construction, we think, is a baseline. And then 3D printing is one of those pathways. It's not the only pathway, but we believe you have to autonomously build before the humans arrive. And that's, I think, probably something that's universal agreement. You know, you have to build the protection before the humans come. But I understand your question about why are we putting all of our eggs and money on the 3D printing when we haven't been able to do maybe as much on Earth when it's easier.
Sponsorship from
Yeah.
manufacturers.
So there's the question, are we being driven by the market rather than by the need?
Yeah.
Yeah, I can answer that quickly. We are a little bit obsessed by it sometimes. And I'll give a small example. The NASA 3D printing competition that you saw, the brief said that we had to 3D print the complete structure and also the structure that will hold the pressurized air. I didn't believe in that. I actually didn't think you could actually 3D print something that contains the breathable air for the astronauts. So what we did with our design, we just had the shell structure protecting for radiation, because that's really what it's good for, and then bring in inflatables underneath it and pop them up, because those were prefabricated really well on Earth. Yeah, we got 10% of our points deducted because we did that by NASA. But I believed in the design process, and I think we sometimes need to be driven by, I think, design more than just technology itself.
Thank you. Last question, then I'm afraid time's against us. Of everything that you've shown us today, I'd love to hear from each of you in turn, what's the first thing that we're going to see?
The first thing we're going to what? See?
Going to see. Of everything that you've shown us today, what's going to happen next?
For space, for Mars, what's the question? What's the first thing you see?
Yeah, how are our lives going to change as a
well, again, I think we see Earth. I think it's I love that, the Earth, you know, the overview effect. It's Earth version 2.0. So for me, it's always back to home again, to wake us up, to remind us of the beauty of this planet. So for me, all of our exploration off planet is just to come back home and appreciate and reflect and try to get it right here.
Thank you. Xavier?
I think yes, that overview effect, because we'll see many, many more people in space. I think tourism, low Earth orbit tourism, that will boom. Those costs are going to go down. Many more people will be able to go to space and experience Earth from looking at it.
Mark?
I think over the last decade or more, the average person's understanding of sustainability and health and wellness on Earth has skyrocketed. And I think over the next decade, the average understanding of what we talked about today is also going to balloon. So I think as a collective, there's going to be more voices, more diversity onto the space mission, and that's going to make sure we don't have a false first step. So I think it's about the kind of social and community around the space program that's changing dramatically, evidenced by the fact that when NASA now hires you, they're at the table. They have an assignment just like us. And that's a completely different model of working a client-designer relationship than we've ever had.
Thank you. Well, look, the three of you have given us a terrific set of presentations, plenty of food for thought, and hopefully much discussion later on this evening. Please join me in thanking the panel and ending this evening. Thank you all.